Hello, it's time for our next big topic, and now we got waves and optics. So I'm doing both of these. I mean, optics, in my experience, tends to get sidelined a little bit nowadays before you head off to university. So I want to bring that back in. I mean, there's so many people who get into physics because they're interested in astronomy, and of course, optics is really important in astronomy. I mean, how far can you get in building a telescope or some eyepieces if you don't know anything about optics? So I want to do waves and optics, but I'll certainly be starting with the waves. And this is also a good point to recap on where we've got to so far in all of the videos. So we started off right at the beginning of saying, well, physics is about matter and energy, which is what the universe is made of. And then we can describe using forces how matter and energy move around. So we've got the motion going on here. So we've got matter and energy plus forces will then give us motion. And we've been describing all of these things. You think of the topics we've had so far. So we had classical mechanics, where we were looking at macroscopic matter in motion. That's really what we were talking about there. Okay, and we started off just talking about, well, how things move around and then how forces can change that motion. I know there are other bits in classical mechanics, but that was the central thrust of it was macroscopic matter in motion. We then went to structure of matter, and we were looking at the subatomic level at what matter and energy have we got. We were just describing subatomic matter, going through our particle physics and looking at the standard model, and then what energy have we got kicking around related to the different interactions. So our forces we were then talking about in terms of interactions, strong interaction and such like, and then having the binding energy, so talking about the specific types of energy that we're looking at the subatomic level. So that didn't have much in the way of motion going on there. It was more just a description of matter and energy and forces. Then we went to thermodynamics, which was looking at the microscopic level. And again, we were describing, well, matter and energy again. So the states of matter, the energy transfer. So we did have motion of energy there, our heat transfer mechanisms, our radiation, our convection, our conduction. We spoke about it a bit, but in a more of a qualitative way, in a sort of hand wavy way of, well, this is how energy can move around. So these are all variations on the same theme. So we've got certain bits to do with matter. We've spoken about matter in every topic. We've spoken about energy in every topic. We've had forces in quite a bit of it. We had Newton's laws in classical mechanics, bringing in forces. We had stuff to do with these interactions, bringing in forces at the subatomic level. We didn't really have forces that much going on in thermodynamics. I mean, it comes up a little bit here and there, but it wasn't one of our primary focuses. But you can see we've got these little gaps. One thing you might think then, okay, with classical mechanics, we've spoken about macroscopic matter in motion. Well, can we have macroscopic energy in motion? What's going on there? Is there something we can describe in that fashion? How can we then talk about at the subatomic level the motion of matter and energy? Because we didn't say anything about that there. So what's going on with subatomic motion? Then we've got things in thermodynamics. Well, we had these things with all this heat transfer and things like that. Well, what's going on there? If we're talking about conduction and we're talking about these particles more or less colliding with each other and transferring energy, you can have this chain of energy transfer of these vibrating atoms or molecules in a substance or a range of substances. So they're not really moving away from their equilibrium position inside the structure they're in, but this energy is moving along. So again, we've got an energy transfer going on there. That is our heat transfer. We got radiation. So this is our, trying to do a gamma there, came out a bit wonky. This is our electromagnetic radiation, which is transferring energy from one place to another. So again, we've got energy in motion. So how can we fit this in to fill in these gaps that we've got here already? And this is where waves comes in. This is energy in motion. That's what we're talking about with waves. We're not transferring matter anymore, we're transferring energy. And this can be done in a whole load of different ways. At the classical mechanics level, we'll be looking at quite mechanical waves. You might have a string. You're playing the guitar or something like that. You pluck the string. The string, it's a macroscopic object. It's moving in a mechanical fashion, but we got a vibration on the string, and this is transferring energy around. So we've got similar things with electromagnetic waves. You've got various waves and descriptions that we have at the subatomic level in quantum mechanics. I mean, we won't be talking about the subatomic in this particular section. I'm going to hold back on that until we get to the quantum mechanics section, and then we'll talk about it there. So we want to be able to pick this up anyway, this idea that we can also just describe energy in motion. It doesn't have to be matter in motion all of the time. We can transfer energy without transferring matter. So that's what's happening in waves. Right, so let's dig a little bit deeper then. So what is a wave? Right, it's an oscillation moving through space, and that's immediately taking us back to our classical mechanics, because we've got some kind of disturbance that occurs. And we'll go through all the different varieties. There's lots of different disturbances you have, but this disturbance can happen, and the disturbance then propagates, unless something else is changing in all directions. Obviously, I can only draw arrows in 2-dimension here, but imagine the arrows coming out at you and into the screen as well. We're going 3-dimensional. This disturbance is just propagating through space. So we've got a disturbance that's propagating through space. And that sounds vague, but as I say, there's an enormous variety of disturbances that you can have, which produce an enormous variety of waves. You've got water waves, sound waves, electromagnetic waves, waves on strings, waves on springs, gravitational waves. There's just loads of them. So we have this sort of vague idea, but that's also shows the power of it, that we can describe all of these things with the same set of core principles, that we've got a disturbance that creates an oscillation. We've already described oscillations in classical mechanics, particularly when we went through simple harmonic motion. And we can describe most of these oscillations pretty accurately, in some cases really, really accurately, by describing the oscillations as in terms of simple harmonic motion. So we'll say these are harmonic oscillators. They're simple harmonic oscillators in some cases. So remembering what the H in the harmonic and simple harmonic motion means, that is oscillations that can be described using sine waves or cosine waves. I mean, essentially they're the same thing. So that is the harmonic. Simple is referring to the number of forces and things involved. It's not being damped. There's no damping or driving going on. It's just an oscillation that's just happening. It's not gaining or losing energy over the course of that oscillation. It's just a simple process. Obviously in most cases that's going to be some kind of approximation. If you're looking at a guitar string, you pluck the string, it eventually goes quiet. It doesn't go on forever. It's not a simple harmonic motion over an extended period of time. It's a harmonic motion. We got a sine wave that's propagating up and down the string. So it's harmonic, but you can't always describe it as simple. But that doesn't mean to say we can't use all of the stuff that we learned in oscillations and simple harmonic motion to describe all of these things. So we need to think about all these different types of waves. Some of them are going to be mechanical. Some of them are not going to be mechanical. We're going to have electromagnetic waves, which are not mechanical, and that's going to make things a little bit more tricky. Then, as I say, this is to do with a transfer of energy, but maybe it's not. And I say maybe it's not because you can get, when waves start meeting each other, it's one thing if you just got one wave, it just starts propagating and it's off through space, and that's great. But then it might encounter something else. Its path will change as it goes through different different medium, it changes from, say it's going through air and then it's going through water, you're going to get changes there. But you can also get changes if it encounters another wave. So we need to know what happens if you've got some wave which is going one way, you've got another wave which is going in the opposite direction or something, they hit each other, what goes on here? Now, if you get particular waves meeting in particular circumstances, you can actually get these things called stationary waves, where you're not transferring energy anymore. The energy gets trapped in a pocket of space and it just keeps going, it just is stuck in there in some fashion. So we need to talk about both progressive waves, which are the traveling waves, essentially, another way people describe them. This is where the energy or the information, because you can think of energy as information, is being transferred through space. But then we've also got stationary waves where the energy is trapped in space. So we need to look at both of those. Then we get to engineering and optics. So, and I've mentioned the engineering there because, light and sound, they're both waves. And it's through the propagation of light and sound waves that most of our communication and perception happens. Everything we see, everything we hear, it's all through the propagation of waves. So that makes it ripe for engineering. In optics, we're manipulating the path of waves through space. So optics, we're normally thinking in terms of light, but it doesn't have to be light. You can have sound waves that you're going to focus and disperse in the same way as you can with light going through lenses. So all of this stuff to do with optics, where we're going to start having mirrors and lenses and things like that, that is what we're engineering in order to control wave behavior for our advantage. The typical focus of engineering, using our knowledge of physics in order to get better outcomes in the world. So there's a lot of that going on, and we've also got this split that we have in all of these topics between classical physics and modern physics, and it's really going to come to the fore when we get onto electromagnetic waves, because they had a nightmare of a job. If you go back to the 17th, 18th, 19th centuries, when they're trying to work out, first of all, what light is, which is one part of the electromagnetic spectrum of waves, they had a lot of trouble working out what it was. And then even when they're in the 19th century, trying to work out how these waves were actually behaving and what was going on caused an enormous amount of trouble. And in the other topics that we've covered, we've managed to get a certain degree of compatibility between classical and modern, and okay, this is how we describe things at the classical physics level, and then this is how we make a simple transition into modern. The trouble with things like electromagnetic waves is they're one of the most difficult features of physics to actually describe in a pleasing, acceptable way in classical physics. You can come up with analogies for how electromagnetic waves are behaving and try and put it in a sort of classical context, but it always feels as though it's lacking a little bit more than we get for some of our other simplifications in classical physics. So we do have a difficulty there, that if you really, really want to understand electromagnetic waves, then you need to be going into modern physics. And I think this is one of the reasons why electromagnetism in first year undergraduate physics really does stretch people. Is one of the most difficult topics to cover when you start moving to university. You've got a lot of things to quite often undo in your understanding of electromagnetic waves. So I'm going to try and get a middle ground in that, as I'm trying to do in most of these videos, of, well, let's not get too many things wrong about electromagnetic waves when we're thinking about them in the context of classical physics. So that's another thing that we need to keep in mind. Right, so just to recap on all of this then, our path that we're going to have, we're going to start with progressive waves. So let's just think simple in terms of this. You've got one wave moving through space. how do we describe this? What's the key terminology that we've got? What's actually going on? What different types of wave have we got? And how are we going to describe that? Then we need to get on to the more detailed wave behavior. So how does it propagate? Then we've got this superposition. So this is where you've got two or more waves meeting each other. What happens when waves meet? So we're going from one wave to two waves now. And then what happens when they interact with each other? Because understanding that is going to give us a much better understanding of the behavior of individual waves when it comes to reflection. So it meets a mirror and it reflects. So we've got some mirror. What's the wave doing? Why is it bouncing off like that? What is going on? We can get a better picture if we know something about superposition of waves, how they interact with each other. The same with refraction. So the refraction is when you pass some light through the glass. So it's coming through air, it hits the glass, it changes direction. What's going on there? Diffraction is the third big wave behavior with refraction and reflection. So diffraction is where you pass a wave through a gap. So you've got some wave which then approaches, and when I got onto the video, I'll describe why I'm drawing the wave differently now. Whereas in these two, I've drawn them as straight lines with arrows, and now I've drawn these lines perpendicular to the direction of the wave. That will be explained in more detail when we get onto diffraction and such like. Hits a gap, and now it's spreading out. So what's happening in diffraction? And all three of these, as I say, are easier to understand if you know a bit about superposition. So we need all of that. Once we've got this basic set of descriptions down of how a progressive wave behaves, then we'll look at the specific case of electromagnetic waves. Obviously, these are really, really important because light and radio waves, microwaves, infrared, all of this stuff, UV, all of these different parts of the electromagnetic spectrum, as it's called, are all really, really useful. So we need to understand a little bit more about what electromagnetic waves are, how they behave in particular, so and how we can go about describing those. So yeah, we do a more or less a detailed case study on electromagnetic waves. Then we've got stationary waves. So we'll be able to pick up that second type. How are we trapping this energy in space? How is this getting set up? How can this also be used? How can we start to release some of this energy from a stationary wave, which is pretty much how musical instruments work. You set up a stationary wave which is nearly contained, but not quite. You need some energy come out, otherwise you wouldn't hear anything out of the instrument. So we can look at what stationary waves are, how they're set up, and then how that is used in something like a musical instrument. And finally, then we get onto optics. So lenses, mirrors, how do they work? How do you engineer those into the different telescope types? How do you, both optical and things like radio telescopes and things like that, how do you create lenses? What are the different lenses doing on telescopes? So it's useful just to have that much better idea of how telescopes work, because people are just really interested in telescopes. Most people would have used them, or if they don't, they might be thinking about it. You get loads of people start buying telescopes when they head off to university or before. So knowing the different types, their strengths and weaknesses, and the theory behind their construction, particularly useful. So as you can tell from all of this is a big topic. This is it's not as big as classical mechanics in terms of how much we're going to have to go through, but there's more content that we're going to have to go through here in waves and optics than there was in either structure of matter or thermodynamics. So this is going to take a while, but it's really, really interesting stuff. So hopefully you'll feel the same when you get to the end of it.